And I'll say hello. My name is David Scher. We are here for Physics 572, Introduction to Health Physics. Today we're going to be talking about systems of radiological protection, which is really about the underlying approach we use for radiation safety and how it came about. So I'm going to get my slides up here. And somehow I'm having trouble with that. So let me start over. I want to put it on this one. Minimize that and share my screen. And these are the slides. Share screen. And here we are talking about systems of radiation protection. And everyone can see this, right? Good. Okay. So first I want to start off by talking about what a profession is. The term profession is thrown around to mean essentially anything you make money at doing. For example, we have professional athletes, professional golfers. So that was at once thought of as a hobby. I guess there are professional video game players too. So anything could be a profession in that sense. But the traditional meaning of the word was professions. A profession is a group of people engaged in a certain activity that requires education and training, and the people in the public depend on that education and training. Okay, so in the earliest version of this, in the Middle Ages, there were three called learned professions that were called. There was medicine, law, and the clergy, and those were people who were regarded as in professions that were not available to the general public. And so the idea of a profession has grown from there. Professions are characterized by autonomy. So in a profession, the profession decides what the profession is. It's not something, I mean, it's the professions are subject to law, but they're nobody decides for the physicians what the practice of medicine is. They make that up. They make that decision themselves. It's self-regulating. There has to be some internal form of controlling behavior so that people conform to the standards of the profession, and characterized by some body of knowledge that's shared and agreed to by the practitioners, and some agreed standards for practice. Sometimes professions have a legal recognition too, but not always. Engineers, for example, have a legal license. They're professional engineering, and the government recognizes that. You can't design a building or any machine or whatever without an engineering license. It's required so that they can guarantee that it's going to be function properly based on the engineer's education experience, and etc. Industrial hygiene, medical physics, public health, veterinary medicine. There are many professions. They essentially operate, as I said, autonomously, and people in that profession are responsible to one another. Now, why do I mention all this? Part of being in a profession is that you agree to abide by the practices and principles of the profession. And so when we talk about standards of radiation protection, this isn't just a matter of personal opinion. This isn't just a matter of preference. This is what it takes, what we agree to do when we join a profession. And so these are our professional standards, or some of our professional standards are reflected in these standards of systems radiological protection. Okay, so we have standard setting bodies at many levels, but at the sort of global level, there are bodies that are recognized as being authoritative for us at the international level and in individual countries. The International Commission on Radiological Protection establishes standards and practices that are recognized, and they in a sense speak for the profession. It's made up of people who are themselves members of the profession and highly regarded. And then there's another unit that's another organization, the International Commission on Radiation Units and Measurements, called the ICRU. They're the body that establishes primarily the scientific basis for how we measure things, how we evaluate things, and they're most active in medical dosimetry. But they do have something to say about radiation protection as well. In the United States, we have the NCRP, National Commission on Radiological Protection and Measurements, and they are the authoritative body that people look to for guidance on practice of health physics in the United States. Okay. Now, historically, I'm going to go through a little bit about how these developed. The earliest safety concerns in radiation safety early on related to primarily use of X-rays. I think I mentioned in our biological effects lecture that there were people who suffered skin injuries and injuries in their extremities because their radiation protection was largely unknown. And so it became clear that some standards of radiation protection were going to be needed, or that people were going to need to protect themselves. I should mention that this information is in chapter 7 of Staben's book, so you can go through there if it's useful to you, because he probably covers it in greater detail than I'm going to be able to. Originally, in the very earliest days, the safety recommendations were ad hoc, fragmented, made up by individuals, different locations. And so in 1925, so pretty early in the use of radiation, there was a large gathering for people working with radiology, with Röntgen rays in the healing arts. In 1925, they had the first International Congress on radiology. And during that meeting, they recognized the need to have some unit for measuring radiation. At the time, people would talk about, oh, we need to limit the radiation exposure to 1% of the erythema dose. But how do you measure that? You get to burn somebody's skin to know what 100th of that would be. And so, and this was in the second Congress, 3 years later, they established a couple of bodies, a couple of committees that eventually became the ICRU and the ICRP for these purposes. And so these became the standard setting bodies. They were established early on. They were well respected, made up of people who had good reputations, and so they established, eventually have become the groups that are looked to establish the standards for systems radiation protection. In the United States, at the same time, there was a group that was under the leadership of Loris and Taylor. He was also a member of the early ICRP, so he was active on the international stage, and thought it was important to have a national body to implement the international regulations in our national context. So he was the leader for many, many years of this effort. The group that was formed in 1929 was the U.S. Advisory Committee on X-ray and Radiation Protection, and this later became the NCRP after a couple of name changes, which is the National Council on Radiation Protection and Measurement. So, how did the standards develop over time? Well, the first thing that was necessary, as I've mentioned a few times, is to have some unit for measuring radiation, so we could talk about these things on on the basis of actual measurements and speak the same language. And so they came up with the definition of the Röntgen in 1928, and that was the ICRU group. The ICRP group came up with some recommendations for safety. And so those standards, however, were not numerical. They were things like stay away from the primary beam, limit your exposure time, general recommendations for radiation safety, but not as similar to what we would recognize as standards today. Now, after this, the early numerical standards that were developed were based on the idea of a tolerance dose. If you had less than a tenth of a Roentgen per day, you wouldn't develop the erythema, and so they thought that all was well and good. No one yet recognized the possibility of stochastic effects, of late effects from radiation. Based on the work with the experience with the radium dowel painters and studies that were done with them, they came up with a limit for internal dose of 0.1 micrograms of radium in the body at any given time. And so, of course, we know that the units, a gram of radium is the same as a curie of radium. So this would be equivalent to 0.1 microcuries of radium in the body at any given time. So the NCRP came up with 0.1 rad per day. The ICRP, about the same time, came up with a recommendation of 0.2 Roentgen per day. And so they're within a factor of 2 of each other, but somewhat different. I believe the NCRP derived theirs first and the ICRP second, but not by very much time. And so, as I said, that the intent was to protect against tissue reactions, largely skin reactions, and these are the values they came up with. These were used during the Manhattan Project. It became the tacit standards used in the Manhattan Project. So it went beyond the use in X-ray work and using radium, naturally occurring materials. So when work began with artificial radioactive material and the first reactors, the same standards were carried over. Okay, in the post-war era, there were refinements to the standards, and these are detailed in Stabin's book pretty clearly. And so after the 40s until in the second half of the 40s, whole body doses were decreased. The limit on whole body doses were decreased from 0.1 rads per day to 0.15 sieverts per year. So they went from what was essentially 25 sieverts per year, 25 rem per year to 15 rem per year. Whole body, the extremity doses were established for the first time, and the limit there was equivalent to about 75 rem per year. These were daily limits, but these were the annual equivalent. They also recognized the importance of relative biological effectiveness when you have high LET radiation, either neutrons or alpha particles. And so the use of RBE was also added by the NCRP during this era. They also developed limits for internal radionuclides. They had one for radium, and so they established, I think it was 10, about 10 max limits for nuclides. And these were conceived to be body burdens, so it's how much activity you had in your body, not in an individual organ. And so they derived maximum permissible body burdens and maximum permissible concentrations associated with that. And so that was the beginning of internal radiation protection standards. The first ICRP publications that were actually published separately as standalone documents came in 1958 through 1960. There were 5 committees, there were 5 reports. The first one established the whole body lifetime limit as 5 times n minus 18. So n is the age in years. So 5 rem for every year over the age of 18. That became the occupational standard at the time. But they also indicated that exposure should be maintained as low as practicable. ICRP established the maximum permissible body burdens again and maximum permissible concentrations. This is largely building on the work of the NCRP that I talked about during the era right after the war. And then ICRP established standards for low energy X-rays and sealed sources. And ICRP 4 talked about accelerators and nuclear particles in a high energy range above 3 MeV. And then ICRP talked about standards for radioisotopes in medicine and research. This was in the dawn of the nuclear medicine era. Okay, the current system of radiological protection has been around for quite a while. It's based on 3 principles: justification, optimization, and limitation. These are in this era of around the 60s. So justification, radiation should not be used unless the net effect of using of that action, the operation, the activity that uses radioactive material does more good than harm. There should be a net benefit from it. Optimization means that even if we establish standards, we should maintain the doses as low as they can be, as low as what we now call as low as reasonably achievable. Social and economic factors taken into consideration. And limitation means that there should be some dose level beyond which people are not exposed. So we should only do things, use radiation when it has a net benefit. We should try to keep the exposures as low as they can be reasonably, and then they should never exceed a certain level. And so in the ICRP recommendations early on were that the effective dose should be no more than 5 rem per year for workers, and there was no lifetime limit at that time in the ICRP system. Organ and tissue doses, including the skin, extremities, and individual organs, should be less than 50 rem per year. Members of the public, exposure to members of the public should be less than 0.5 rem per year, so 0.005 sieverts per year. In addition, they established secondary limits, as I said before. This is for ICRP 26, established the secondary limits for ALIs and DACs. I don't know why I didn't put the number in here. This is report 26 in 1977. NCRP guidance around that time in 1975. So ICRP 26 with all these new standards came about in 1977. 2 years later, the NCRP issued a report number 43, saying that they didn't need any changes and essentially didn't want to go along with the new ICRP system. However, around that time, U.S. government agencies decided to follow the ICRP 26 system. So the EPA, the DOE, and the NRC, and that sort of forced the NCRP's hand. And in 1987, they adopted recommendations that were consistent with the ICRP 26 recommendations. Okay, and so these standards were revised in 1960. The basic principles of the system of justification, optimization, limitation did not change in 1960, but some of the details did. They retained the 3-part system. I've mentioned before, I think, when we talked about internal dosimetry, they defined the radiation weighting factor to replace Q. Q is based entirely on LET, WR is judged based on epidemiological data. Let's see. They refined the values of the tissue weighting factors. They expanded the number of them and changed some of the values. They established a concept, or they replaced the name of effective dose equivalent, replaced it with effective dose to indicate that they were, it made it clear which concepts you were using, which standard, which coefficients and which approach you're using. They did change the limits, so that there was a three-part system with limitation, but in 1990 they changed the limits. So the dose to workers should be limited to 0.1 sievert over 5 years. You still were basically limited to 5 rem per year, but it had to average over a 10-year period, had to average 2 rem per year. And the effective dose to members of the public was decreased from 500 millirem per year, half a rem per year, to 100 millirem per year. They also added the concept of dose constraints. Those are values that are considered appropriate for a given operation. Dose constraints are somewhat lower than the standards. They're seen to be a guide in planning and decision making. So we should only, they're considered to be readily something that's achievable. So we shouldn't consider operations or alternatives that would exceed a dose constraint. It's not a regulation, but it's a planning guide and a way to help with ALARA. This is a graph showing how the radiation standards changed over time with that history that I showed you up until the 1990 changes. It doesn't have the most recent changes. This is the annual occupational limit, and this shows the public limit, 500 millirem for infrequent exposures. And they said that for continuous operations, public exposure should be limited to 100. This all became 100 millirem with the 1990 standards. Okay, since then, there has been further refinement. ICRP 103 gave some, in 2007, some further refinement to WR and WT values. They've retained the concept of dose constraints and reference levels, but there's a lot more emphasis on it in ICRP 103. Because they changed the values of WR and WT, they had to recalculate secondary standards, the ALIs and DACs, based on those new standards. Okay. So the definitions of the kinds of exposures that were used that fall in these recommendations are occupational standards that are occupational exposures are exposures that are given to workers as a result of their work. So if a worker goes out and has a medical procedure that results in them having, say, taking some radioactive iodine for a thyroid condition, the doses that are due to the medical procedure are not counted as occupational exposure. Exposure due to background radiation, even though you receive this background radiation while you're at work, is not due to your work, and so it's not considered occupational exposure. Radon exposure, even if it's received in your workplace, is not regarded as occupational exposure. It's only work that's incurred directly related to the work you're doing. Public exposures are all exposures other than medical, and medical exposures aren't counted in the public doses, and occupational exposures aren't counted in the public dose. Even though you're a member of the public, the dose you receive at work doesn't count toward the public exposures. Doses received to patients during procedures are not regarded, are not subject to limitation. It's a different class of exposure. The same thing for volunteers in medical research. There are no limits associated with this, but it's a different class of exposure and doesn't count in the other exposure categories. Okay. In addition, there's a concept, an approach is used. In addition to the annual limits that we've described, it's possible for a worker to have a planned special exposure situation. This has been around since 1977 recommendations. So you have an annual limit of 5 rem per year, but if there's a need for a greater exposure for some particular operation, and it's not the result of some accident or something uncontrolled, it's possible for a worker to receive a radiation exposure as planned special exposure. It counts in a separate bank, if you will, of dose. It doesn't count against the annual exposure, but there is a lifetime limit for planned special exposures. Another class of exposure are emergency situations. So if there's, we talked about, if there's some accident, if there's someone steals a radioactive source or uses it for some nefarious purpose, those exposures do not count as occupational exposures. They count as emergency exposures, and there are separate standards that apply to those. The other thing that these standards recognize is if you have an existing exposure situation and the standards change, then the previous exposure situation should be grandfathered. It should not be Herculean. There shouldn't need to be a great expense taken to achieve compliance with the new standards. So when the standards for the public went from 500 millirem per year to 100 millirem per year, it wasn't necessary to go and backfit all the x-ray rooms in every hospital with additional lead to achieve the new standard. Okay. Now I'm going to go over the current NCRP recommendations in NCRP 180. The structure for this is that there are, they recognize 3 groups of exposure situations: planned, emergency, and existing situations. That's very similar to the structure from the ICRP in the past. There are the planned exposures count as separate category of exposure. And again, under the new NCRP recommendations, employers are allowed to provide to use workers above the annual limit, and for a planned necessary exposure, and those exposures are banked separately from the annual limit. Emergency situations call for different dose standards than normal working conditions, and existing exposures should be grandfathered and not be required to retrofit. There are 5 categories of exposures in the current NCRP. Occupational exposure, very similar to what we've seen before. Public exposure, the definition is very similar to the ICRPs. Medical exposures, again, very similar. Exposure due to medical treatment to the patient, or for volunteers in medical research, are a separate category of exposure. And emergency exposures fall into a different category and have their own standards. We'll talk about those in a minute. And they added another category of non-human biota. So in considering environmental consequences of exposure, the non-human biota have their own separate standard of exposure that needs to be considered in designing. There are 3 principles that are very much like you've heard before for radiation safety: justification, optimization, and limitation. Although they call limitation now numeric protection criteria. Justification is the same as before. Has to be a net benefit to society. Optimization, exposure should be maintained as low as they can be, given all given social and economic considerations. And the limitation part is there are caveats in the new NCRP recommendation of when limits should apply. They should apply if the source is if an exposure is well characterized, if it's a stable source, and there are strategies for control that can be planned. So radon exposure is an example that they use for exposures that are not suitable for numeric protection criteria. They vary from place to place. They're not stable. They vary from time to time, and there aren't strategies to use that can be used to effectively control the risk under all circumstances. So the standards for in NCRP 180 are that the occupational exposure, the annual effective dose should be less than 50 millisieverts per year. So that's a little bit for workers over age 18. Workers under age 18 should be kept to 1 millisievert per year. So that's similar to what we've seen before. They do have a lifetime limit, a cumulative effective dose limit of essentially 1 rem per year times your age in years. So it used to be 5 rem per year over the age of 18 when I first got into the business. And now it's 1 rem per year times your age in years. It's an attempt to ensure that the lifetime exposure is kept in check while providing some flexibility on individual years up to 5 rem per year. There is still a possibility of a planned special exposure. Members of the workers that are below 18, 1 millisievert, 1 millisievert per year. It's the same as the public. Exposure to embryo fetus for pregnant workers is limited to 0.5 millisieverts per month throughout the gestational period. And dose to the skin or extremities is 0.5 gray per year. Now, I'll make note that they say that this is in gray. This is not sieverts. That's because we're talking about stochastic risk. The sieverts now have a tissue weighting factor that's based on stochastic risk of cancer induction. The endpoint we're trying to protect against here for individual organs and extremities is not a stochastic risk, but it's a tissue reaction. Same thing for lens of the eye. The standard for lens of the eye is in the CRP regime is a little bit lower, 50 milligray per year. So that's less than what it has been before. Another category of exposure is public exposure. Individuals should be limited to 1 millisievert per year for each radioactive radiation source. Newly discovered sources, for example, when radon was first discovered, it was a big thing because it wasn't well characterized. So if some new hazard, that new radiation exposure, source of exposure to the public is recognized, then action is required if it's above 20 millisieverts per year in that first year. Radon mitigation is a public exposure is recommendation for radon is mitigation should take place if the exposure is greater than 300 becquerel per cubic meter, similar to 4 picocuries per liter. That's the airborne concentration of radon. And for members of the public, exposure to skin, extremities, and lens of the eye, the NCRP recommendation is that the standard for members of the public should be the same as occupational exposure. And the reason for that is we're protecting against tissue reaction in those cases. And the theory is that if the dose is below the threshold for tissue reaction, there's not going to be any negative consequence. And so that's the reason for that. Okay. They have the other classes that they of exposure. Let's see, categories of exposure, I guess is category exposure. Medical exposure, there is no limit for exposure to patients. The benefits, patients receive a direct benefit, and so they offset the risks of any exposure. Caregivers should be limited to 5 millisieverts per year. Members of the public who are not caregivers, employees at hospitals that are not classified as caregivers, but are rather more members of the public, should be limited to 1 millisievert per year. And there are no numerical standards that apply to research subject, but they give qualitative indicators of what kinds of research are warranted for different levels of exposure. So look into NCRP 180 if that is useful for you. Dose standards for emergency workers for life-saving activities. The dose should be less than 0.5 gray. So that's 50 rem for an activity that's life-saving. Notice again, it's expressed in gray because we're protecting against acute radiation syndrome in this case. We're not using sieverts because we're not looking at stochastic effects. For non-life-saving operations that are important, like rescue and recovery phases, emergency workers should be limited to 100 millisieverts for that. Optimization applies. These standards are limits, but we should do everything that we can to keep exposures low with all the operational factors taken into consideration. Okay, now rather than me trying to explain the reasons for these standards being where they are, there are philosophical standards and ethical bases for these standards. I'm going to ask you to watch a video by Chris Clement, who's the executive director of the ICRP. It's provided here. It's the page that I'm pointing you to is let's see if I can get it up here. On the ICRP website. That's the wrong one. Here it is. So I will bring it over here. So the page I'm sending you to is on the ICRP website. It's right here. So there's a description of the system of radiological protection. They have links that describe what the system is, the objectives, the principles, justification, optimization, limitation, categories and situations. And then there's a video at the bottom. I'm going to ask everybody to watch this video. This page has a link to it. It's presented in YouTube. So I want you to watch this in either form. We don't need to see the ad in YouTube, but that's what I'm going to give you as an assignment. I'm not going to do another lecture. I'm going to let you spend your time looking at Chris Clement's description of this, and then we'll have an assignment based on what he has to say. Okay. Do I have any questions today?
Going back to what you said about accounting dose in different categories,
right?
What are some practical consequences that could have? I mean, would that ever come up where like someone is a radiation worker or medical worker, and their public dose or themselves being a patient, they went over their limit for
the
that
medical dose? Yeah. Well, you have
and then
to
they can't come into work, something like that.
Yeah. Well, you have to be careful. So the basic idea is that we don't let that happen.
Yeah.
Okay. So, and I've been in a situation where a worker had medical. There are several aspects. So let's talk about. One is a worker I worked with thought that because he's receiving a dose from a medical procedure, that should change what his exposure is at work, and that's just not how it works. They're regarded as separate and managed separately, and you're not, if you go off and get a medical, even in the necessary medical treatment, it's not going to change your work conditions. It's accounted completely separately. The other thing is, if you're exposed because you have some very small environmental exposure because of where you live, right? You live near some plant, That's not going to count for your occupational exposure either. We have separate buckets, if you will, where we put these doses and they don't count against each other. Does that help? So the whole point, I think the main point of this is to make it clear that these things don't count against each other. Go ahead. You have a question. You have a question. You're going to say something, Alex.
Oh, I was just saying, so basically it's really not going to come out in a way that it's going to keep these people out of work. Right?
It's going to be the other way around. The worker's going to want to say, I can't come into work.
Right.
It's more making it clear that these things are separate and distinct. So it's not going to, you're not going to have to stop somebody from coming into work. You're going to have to convince somebody that they have to come to work, even though they have a medical procedure.
I will say too, Alex, like where I work, because of how you monitor people, right? Like if they get a treatment and then they go to wear their TLD, we actually can't have them wear their TLD because then we're recording a dose that they're not actually getting at work. So we'll restrict them in the sense of you can't get your TLD back until you're reading background on the outside.
Yeah.
Then
you don't want to misapply doses that are from different sources. Another approach is to give someone a temporary dosimeter if they're worried about, depending on where they work. If they're in an environment that doesn't typically have dose, you can probably get away without monitoring that period, right? But if they're in an environment that they're going to have exposure, you might give them some way of something that doesn't add to their cumulative record, but you can somehow separate out the work exposure from the medical exposure. It's going to be difficult to do. It's going to be difficult to justify that we know this was your background medical exposure. Does anybody have any history or any war stories about dealing with people who've had medical treatments and then had to have dosimetry as well?
I had one person come in, and when you come in, all of our TLDs are all right there for everyone across the site. And they came in right after getting, I think, like a stress test done with technetium 99. And so they were walking 100 millirem per hour count, and they walked past everyone's TLDs.
They added up to everybody, and high exposures. That's not considered a high exposure for the procedures they're getting, but it's a very high exposure for work, right? So, the reason is you're assuming somebody's going to be working every day for a long period of time, and that's going to accumulate. But you only get one medical procedure maybe in your life, and so it's not going to. Yeah. Well, that's another example of how it's going to complicate your life.
Some medical procedures effective for a couple of days. We've had people come in and they're like, well, my doctor said I was supposed to see clear by now. It's like, but your doctor doesn't realize where you work, and you can't pass my portal monitors. I can't have you going in.
Right.
Or we dealt with guys having stress tests and they're out for a few weeks. We had doing cold work for a while and actually like put them at a desk outside away from other radiation workers, so they're not their TLDs.
If you can give them other duties, that's good.
And then I had a friend who had cancer, and he said he actually like set aside a separate bathroom for himself at his home because they have young kids, and he got his own survey meter, and that's what he used to check himself at the house.
Yeah, he did it for himself. It's not something that anybody required of him.
That was for himself, exactly.
Yeah. So that becomes a problem in hospitals as well for the staff, because people receive 100 millicuries of iodine that they take by mouth. They pee that stuff out voluminously. So this is someone who's had their thyroid removed. So they don't have a thyroid, but if they have thyroid cancer, they might have thyroid metastases throughout their body, right? So they could have thyroid cells in their lungs or in their liver or whatever else. And so they give them a large amount of iodine. 100 millicuries is not uncommon. 300 millicuries is I've seen. And so it's taken up by all these individual metastases, these very small masses. But that's a small percentage of the overall thing. When you take iodine into your body, a third of it goes to your thyroid. Maybe a half of it goes to your thyroid, depending on your particular physiology. But in this case, the uptake might be 1% or 2%. So you've got 100 millicuries, and 98 millicuries of that's going to come out in the urine in the next couple of days. And so, or sweat or feces or anything. So everything in the room becomes contaminated. They touch the telephone's contaminated. The remote control for the TV is contaminated. The rails to the bedding, the toilet seat, everything becomes contaminated. So this is go ahead.
Said lunchrooms.
Yeah, well, if they're hopefully the patients aren't going to the lunchrooms, but
right.
Yeah.
Well, if they go back to work.
Right. Well, no, if you get 100 millicuries, you have to stay in the hospital.
Yeah, the release
Only
rate for the
allowed to
hospital
leave.
is 2.
Pardon me?
The release rate is 2 from like a meter is what you
Right.
have to be reading to like.
You're
leave.
allowed to
Manufacturing. I don't know those rules, so that's good to know.
yeah, you're allowed to send somebody home if the amount of activity in their body is less than 30 millicuries. So you can give someone who doesn't have cancer, who doesn't have this condition I'm talking about, just has hyperthyroidism. So the thing about hyperthyroidism is we don't know how to treat doctors don't know how to treat hyperthyroidism. So they give you radioactive iodine to make your hyperactive thyroid into a hypoactive thyroid. So you have a thyroid deficiency, and they know how to treat that. So they trade one medical condition for another that they know how to treat. So you can give somebody up to 30 millicuries, 29.9 millicuries, and send them home that day. And that's when they're in the lunchroom. That's when they're causing all this, potentially contamination. But that's what. Go ahead.
Yeah, because that's just nasty.
Yep.
The radio sensitivity to that for production, I've heard all kinds of horror stories, and we're never making that again.
It wasn't too long ago that they were letting patients, instead of sleeping it off in like a pressurized room, they were doing it in like a hotel. And they were having at least. So I used to work at a hospital down in Texas.
Yeah.
And they had to move it into the hospital, obviously.
Right.
Because we're having massive issues at the hotels. And then if you're not treating everything properly and decontaminating everything properly, especially like if the floors aren't sealed properly, that room has to be shut off until you can go back in safely.
Right. So
air filtering and airborne and outside. Oh my God.
Yeah, because it can be volatile, right? It's iodine. So the only benefit here is that the half-life is 8 days instead of 300 days. So it's not going to be there forever, but it will be a significant amount of time. If you own a hotel, closing down your room for 80 days is a big deal. So yeah. Anyway. Other questions about the standards? Now, I should also mention that the ICRP is in the process of reevaluating the standards of radiation protection. They've had a series of meetings over the last few years where they've had people express views about revising the standards of radiation protection, the systems of radiation protection, including the standards. This gets, so many people in health physics think there should be some minimal level of exposure below which restrictions are not important. And so that's becoming part of this whole LNT issue, is becoming part of the debate, or has been part of the debate about what the systems of radiation protection should look like. So keep your eyes open to news in the ICRP world and the NCRP world about any revisions. The last few revisions, the changes to the system of radiation protection have largely been small changes to the tissue weighting factor, small changes to the radiation weighting factor, things like that. It's possible that there could be a more extensive change to the way we do business.
Well, but the big occupational question is the NRC. What are their changes?
Yeah. Right. Just because there are changes in these professional, again, we as health physicists are obliged to live within the standards of our professional. The government is not. So
I agree. It's just, I mean, I work at one of the most significant manufacturing site, and dealing with our maximal dose it's difficult. And
Right.
we try to follow the international standards, but that's causing other issues right now.
Right. Yep. So the way this class is structured, you might be able to see it by this point in the career, is our lectures are keyed to classes in the curriculum. So we started off with radiation physics classes that are similar to physics 571. We had we're talking now about standards of radiation protection. Next week we're going to talk about regulations. Those are similar to physics 573. So as we go through the course, and we talked about dosimetry, which is similar to physics 576. As we go through the course, this introduction course touches on topics that will be going into more detail in other classes. And so when we get to physics 573, we'll talk about the difficulty with regulation enactment, how they have to promulgate regulations, how that the complications there, and maybe some of the factors that go into whether there's going to be a change to regulations. Okay. Other comments or questions? Okay. Well, thank you for your attention. Do you have any questions about homework? Anything that I can tell answer on a larger front than just this lecture?
If anyone has the YouTube link handy, you can post that in the chat.
I will do that. I will do that now, and I think that when people watch this, they'll be able to see it as well. So where is the YouTube one is right here. So we had a lecture from this same person, Dr. Clement, at Illinois Tech, and we had a recording of it. And in the past in this course, we've had people watch the recording of the lecture he gave here. I can't find it. I think it's just been so long that it's no longer available in our archive, but it's similar to this video, and that's why I'm asking people to look at this video. Okay. Other questions?
No, but I do have at the very end of the lecture, I have a thing from today I'd actually love to talk about. So, but that can be at the end of the lecture.
We're done. So talk about it if you like.
I thought you had the 7 p.m. that we're starting. Are you totally?
Oh, because I'm asking you to watch an hour-long video, I'm not going to do another
okay.
Lecture. I didn't realize it until I had already scheduled those. Go ahead.
So I was just kind of a experience from today. So we have we have 5 current cyclotrons, and most of them have 3 of those machines have 4 or 6 target stations on their own. So we use augmentees. That's what the term we use on our site for personnel who come in to do some of the maintenance work, so that our cyclotron operations group doesn't get all of our dose, because our cyclotron operations and chemistry groups are the ones that get the most dose on our site annually. Yes. So we have other people that we use to come in for doing that. So I as an HP, that's one of the areas I primarily support. I'm pretty mechanically capable, so sometimes I'll have to kind of go in and help out, so I can keep the PSYOPs guys out of there, so that I'm kind of in the medium range for that. But like the lady we had today doing the work, she's not incompetent, but she was struggling with some maintenance work, so she got 260 millirem today. If I or one of the PSYOPs guys had done it, we probably would have gotten definitely under 150. I would think even closer to 100 millirem per dose for the maintenance work we were doing. But realistically, we still need to use her, because she's going to save us that dose so we can use it for all the other times we're going in. So it's just kind of the thought. It's kind of more of a, like, that's how we process so that we can spread the dose around. But sometimes you also get more overall total man rem, because you're using less experienced.
So unintended consequences, right?
Yeah, exactly.
Yeah,
so I kind of want to hear your thoughts questions about that kind of circumstances. Like clearly, I feel like we're following the right process, but like I think we should probably do more to help out with, giving people practice with wrenches in a safe
Right.
space.
I was going to say that one thing you can do is dry runs, right?
Right.
But you got to pay them for that then.
Well, and we're understaffed as a site, and that's not going to change anytime soon.
I understand. I understand.
Yeah,
So
because
they had more work. They do this at power plants, of course, during outages all the time.
outages are special because usually have specialized people coming in to help out. And the thing I've worked at other sites where they're like, well, you have, you assume 20% of anyone's time is spent on training or on vacation as a minimum. So if you're properly staffed, you're staffed 120% for your daily workload. So if we were at that, then we could have training, then we could have more hands-on mechanical wrenches. Not like she doesn't understand how to use a wrench, but I have met people who do not understand that you can flip a wrench back and forth and other ways to manipulate it. And oh my God, I've had to work with those people. Oof. She's not incompetent. She was just less competent.
Well, and inexperienced probably. Maybe tomorrow, if she has a job to do, she'll understand you can flip over the wrench. And
she didn't have an issue. Like she was pretty comfortable with the wrenches. She ended up struggling with because sometimes things are lefty, loosey, righty, tighty, and sometimes it's the general style, but especially this kind of stuff where you have two screws at the ends, you have opposite directions too.
Right. These are moving parts, and so they might have to be threaded the opposite way.
Exactly. That was just kind of a food for thought on you save your main high dose groups, but sometimes you end up giving more dose over, in total to someone who would give less normally.
So in the hospital, there's a debate, maybe not a debate, but a practice where when if a baby needs to be held, they will ask the parent to hold the baby for the x-ray because the workers are there every day doing this, and it would accumulate a higher exposure. It's the same amount of exposure to the population, right? Whether the x-ray tech does it or whether the mother does it, or the parent does it. But because of the way we record doses and what counts against what, we end up asking the family members to hold the baby for the x-ray instead. It's, I think, similar to what you're talking about with the Radiotech.
It's similar, but the benefit with having a family member hold a baby is the baby's more likely to be calm and less moving.
But the other side is that the family member may be more anxious about radiation than the x-ray tech is. Most
people seem, from my experience in medical circumstances, people are used to getting x-rays for teeth, so they don't think anything of it.
Right. In many cases, yeah.
But it was just a kind of food for thought. Like
it is an unintended consequence. It's just part of life that we have to live with.
Yeah, but I can't let my cyclotron specialist get that dose because we try to follow the international standard of averaging 2 rem per year, and guys are at those levels. So if I'm not managing that right, then they're gonna go over, and that's not what is allowed currently at our site.
Yeah, and they're trying to sell in Europe, and so I understand the reasons they might want to do that. Okay. Anybody else have a story? So I'm going to turn off the recording then. Thank you for your attention. And then let's see, how do I get this recording stopped? There we go.